So let's do a few things here. So what we're doing is comparing what happens when the electron behaves as a particle versus when it behaves as a wave. So let's do this. Let's consider a particle that is essentially oscillating, quote unquote, between two boundaries, right? Oscillating between two boundaries. All right. Oh, by the way, let me, I have some guests who arrived late. I'm going to try to get them in. All right. All right. So that would be this guy. Let's say they have this. This is a particle of mass m. And it's basically going back and forth between two boundaries. Well, we know from our study of energy that this particle would have a kinetic energy that is given by 1/2 times the mass times the square of the speed or the velocity, right? Notice that in this case, this energy would have a value anywhere between 0 and infinity. And I'm going to put less or equal than, because technically, if the particle stops and does not move, it has 0 kinetic energy, right? So that's the range of the kinetic energy. Not only that, but if I were to say, what is the probability that if I take a snapshot of this particle at any point during its trajectory, what is the probability that it'll be at a given position? So let's say I do a graph, and I'm going to say this is the probability of the particle being located at a position. Let's going to call it, X. So let's say we can be anywhere between 0 and L, which is the distance between the two boundaries. So basically, it would be pretty uniform. In other words, the particle could be anywhere in here, and any position in here has equal probability. So any position, equal probability. And if I did like a stop motion video of this, I would be able to see the particle at any one of those positions. So if I do stop motion video, I can see the particle, right? Like, guys, I know when you watch a baseball game and they do a slow motion video of the pitcher, and you can see the ball slowly making its way into the catcher's mitt or into the batter's bat, either one. And you can actually stop the film, the motion, the video there, and you can see the ball just sitting there, basically floating in air. But you can see it. You can track every position that ball goes through as it travels from the pitcher's arm or hand into the catcher's mitt, right? Now, let's change the model now, all right? Let's consider now a stationary wave, okay? Let's consider now a standing or stationary wave. Again, oscillating between the two termini. Let's go ahead and use this model here, the first harmonic, all right? So here's my boundaries. And here's my wave. So it's coming in, it goes up, and then it goes down, right? And of course, it's going to bounce back like that. Okay, according to the Broil, the equation we just saw, and I think it is pronounced that way. I kind of looked it up a few years ago, but the wavelength of this thing is actually h over mv, right? So that means that the speed would be h over the mass times lambda. I'm just rearranging that equation. Remember, lambda is the Greek letter that we use to describe the wavelength, right? Now, let's see what the energy of this quote unquote wave would be. So the energy would be 1/2 mv squared. So that would be 1/2 of m. And I'm going to substitute this in here. H over m lambda squared. Sorry, this looks like a 2. It's actually a square there. So if I kind of like clear all that out, I'm going to end up with an expression that looks like the energy would be h squared over 2 times m times lambda squared. Now, remember this. Remember that we said, let's say for this harmonic in particular, the one where you have a wave coming one way and then coming another one, we said that essentially for these things, the wavelength was going to be always something like 2L over n, right? So in this case, because n equals 2, that means that lambda equals L. So we had derived that expression earlier on, right? So let's go ahead and plug this in here. All right. You know what? Let me put some steps in here. Okay. So here is our thing. Here's that. 3, 4, just so you can keep the sequence of steps here. So what we're going to say here is that the energy, if I now go ahead and come in here and I take this and I plug it in here, right? I'm going to get that the energy is h squared over 2m times 2L over n squared, which ends up saying, I'm going to rearrange and solve all these squares and stuff. So I have n squared times h squared over 8ml squared. So there's several things that come out of this, okay? Let's make some observations. A, because n has a specific number, 1, 2, 3, etc., that tells you that E only has discrete values. In other words, the energy is quantized. Remember that if the electron behaves as a particle, the energy can have almost any value. It all depends on the speed or the position where it's at. But if the electron is a wave, the energy is quantized, which is what the model of the atom was proposing, that the electrons could only have certain specific values of energy, right? Secondly, according to this model, because nothing here is 0, the energy can never drop to zero. Remember that in this case, if the particle stops, the energy becomes zero because the velocity is zero. But in this case, notice that there is really no velocity term in here. It doesn't have anything to do with how fast this thing is traveling. So therefore, because of that, then that means that the electron doesn't collapse into the nucleus. This is pretty cool. As a matter of fact, I'm going to get another piece of paper here, and I'm going to expand on this again. So I'm going to come over here. I'm going to write this equation again that we just did. Okay, so we said E equals n squared, oops, sorry, not too far up, n squared times h squared over 8ml squared. Okay, so point number C. Let's see what these values are. Let's take, for example, for n equals 1. So that would be technically 1 squared h squared over 8ml squared. Remember, that's the lowest value you can have. You can't have anything that goes, to zero. It doesn't go to zero. So E2 essentially would be 2 squared h squared 8ml squared. But since all of this unit is E1, so this means that this would be 4 times the energy of the fundamental harmonic. E3, if you continue extending this, would be essentially 3 squared, so 9 times the initial harmonic. Right? So in other words, if I were to do a diagram of these energies, let's say I start here at n equals 1. Notice that they don't increase in typical multiples. So the first difference is 4 times what this is, so over here. But the next one is going to be, a little more than 2 times the previous one. The next one is going to be much less than twice this one. So, right? So you can see that it generates exactly the same energy diagram that Bohr's atom had. So it's the same energy diagram as Bohr's. The difference is that in this case, the energy has been calculated from a study of the harmonics of an oscillating wave versus from Bohr essentially plugging in numbers he got from, remember I told you about the studies of Rydberg and Balmer, just basically kind of like hammering in equations, making them work. Okay, the other thing that you see is, notice that the energy also depends on L. So imagine if the wave is oscillating in different boundaries. So if different atoms, oops, sorry, put this up. If different atoms have different L's, which remember, we are in this case kind of like trying to make an analogy between a particle, a wave oscillating in one dimension. But remember, in the atom, we're talking about an electron oscillating in a circular dimension. So this would mean that different atoms have different ways of confining their electrons. So it's different atoms have different wave patterns. And therefore, they're going to have a different emission spectra. Remember we talked about last time how different, you have helium, you have neon, you have hydrogen, they have different spectra. Well, of course, if different atoms have different L, which means probably size, you are going to get different spectra. And maybe that's why the model of Bohr could not predict the emission spectra of other atoms, but it still works. In other words, at least within these confines, it still works. All right. Okay, let me get a few seconds to absorb that. I know that was a lot of math. And let's come back to one more thing, and then we'll take a short break, okay? Let's come back to our PowerPoint here. Okay, so this is what we said was that according to de Broglie, the reason why the energy of the electron is quantized is because it's behaving as a standing wave, oscillating on a circular trajectory, for which there are limited wavelengths that you can associate with it, and therefore limited energy levels. So that's why the energy is quantized. Now, of course, here's the question you're going to ask. How come we don't see that? In other words, you're telling me that everything that we're made of, these atoms, they behave as waves. And other than the expression, cool wave or que buena onda that we say, other than that, we don't see any wave properties in matter. Everything we see behaves as, classical physics predicts. So let's see if we can apply. Let's see if we can apply this. Okay, let's consider a ping pong ball. What would be the wavelength of a ping pong ball, 2.5 grams, traveling at about 35 miles per hour, which is 15.6 meters per second, which, by the way, I looked up the record. The official record is somewhere around 70 miles per hour. That's as fast as somebody has been able to hit a ping pong ball. All right. So we're going to calculate what is the wavelength of this, particle / wave of ping pong ball. All right. So this is the de Broglie equation. Now here's the problem. We have to be careful with the units, right? Because the Planck constant was given to us in joules times seconds. So we had to go back to the previous chapter. We defined what a joule is. And we said that a joule is a unit of energy that corresponds to the work done in moving a mass of 1 kilogram over 1 meter at a 1 meter per second squared acceleration. So in other words, if we fix the units here, we can write the value of H in terms of kilograms times square meters per second. All right, so that's very important. The other thing is we have to then put the mass of this thing in kilograms, and we have to put the speed in meters per second. Fortunately, they gave us that one already, but now we have to figure out what is 2.5 grams, right, in kilograms. So let's see what that is. So the mass in kilograms and the speed in meters per second. So lambda would be, again, Planck constant is 6.63 times 10 to the negative 34, again, joule seconds. But you saw here where we have the adjusted units, right? Have them in there. So let's write this out. So 6.63 times 10 to the minus 34 kilograms times meters squared per second divided by mass, which is 2.5 times 10 to the negative 3 kilograms times 15.6 meters per second. So, so the per seconds should cancel out, right? The meters should cancel out with the square meters here, and the kilograms should cancel out with the kilograms there. So you should be left with units of meters. I'm just going to go ahead and plug in the number. I'm not going to waste time doing the math. So what we have here is 1.7 times 10 to the negative 32 meters, which is 1.7 times 10 to the minus 23rd nanometers. Now, you all know that a nanometer is a very small amount, right? It's a billionth of a meter, right? So there you go. That is the wavelength of a ping pong ball. But you know what the problem is? Problem is, an atom is roughly about 0.1 nanometers size. You're talking about something that's like 22 orders of magnitude smaller than that. There is no device that could detect that kind of a wavelength. So the point is that even if matter does have these wave properties, we're not going to see them in the macro world. You only see them in the atomic world. Why? Well, because this constant here, with this 10 to the minus 34 in there, can only be offset by a very, very small mass in here, by something that's 10 to the minus 28, 10 to the minus 30 kilograms. And that's what subatomic particles are. So the only way to make this equation give me a wavelength that is reasonably detectable is if the particle is incredibly, incredibly small and light, okay? So that's pretty much the point here. So, of course, the question that comes up is, how do we prove it? How can we show that this model is correct, right? So what we're gonna do is, we're gonna take a 10-minute break, all right? And when we come back, we're gonna tackle that question. What is the proof that electrons do behave as waves, all right?